Exam review question related to NMR analysis. Deduce the structure of the compound whose spectral data are shown below. Provide the degree of unsaturation du in the space provided, and label the location of each signal from the proton NMR spectra using the letter for each signal. Alright, let's get into it. So the first thing I suggest you guys do when solving NMR problems is always to just observe the spectra that's provided and cross-reference it to the formula that's given. So we see we have 7 carbons, but if we count up the number of carbon-13 signals, we only have 6 of them. So even though there is no integration of signals when it comes to carbon-13 spectra, we know that higher intensity could indicate not integration but equivalent carbons. So it shows up as just one signal. With proton NMR, integration is possible. So we know carbon makes 4 bonds, but definitely not 6. So a high intensity signal here, like a 6H doublet, often indicates 2 methyl groups. So using the molecular formula, the first step always is to calculate du. So we have 2 oxygens in C7H12O2, but since oxygens don't count, we just ignore them. We then divide by 2, and we find du is equal to 2. So a du of 2 could be an alkyne and a ring, or an alkene and any sort of acid derivative, like a carboxyl, an ester, and amide, or it could even refer to an alkene and any sort of carbonyl. In order to narrow down our options, we need to observe the spectra. So let's look at carbon-13 first. We have a signal at around 170, and we have 2 signals in between 100 and 150. If we cross-reference that, most probably we have an alkene and an ester. In combination, satisfies du of 2. But the question is our alkene terminal or internal? And is it near our ester or not? Well, then we just refer back to our proton NMR spectra. One dead giveaway is that signal F has a doublet of triplet. This kind of complex splitting is only possible with a terminal alkene. It's around 6.1 or 6.2, which means this terminal alkene is most probably near the ester. Now, in order to piece together the structure from the data, we need to analyze each of these individual signals from the proton NMR, A through F. Now, in signal A, we have a 6H doublet, and because this signal is of high intensity, it's most probably an integration of 2 methyl groups. It's an isopropyl because these methyl groups here have 3 hydrogens each, and because they're adjacent to only 1 hydrogen here, it's a 6H doublet. We can cross-reference the isopropyl by looking further down the spectra at signal C. We have a 1H septet, and it's a symmetrical signal in terms of its splitting pattern. That's one clue. The other is the splitting pattern, septet, meaning we have 6 neighboring protons, which are these methyls. So together, A and C represent 3 carbons out of the 7 that are given. Now signal B is a 2H doublet. We have 2 hydrogens involved, and there's only 1 adjacent hydrogen. So the only way to satisfy 2H doublet is that our protons only have 1 adjacent hydrogen. And this carbon can't bear any hydrogens. So I'll represent X and Y as 2 other groups that are non-proton bearing. So most probably, these 2 hydrogens are directly adjacent to the alkene. And that could be cross-referenced here when we look at the allylic hydrogens, the ones that are directly adjacent to an alkene, 1.6 to 1.9. That CH2 group can also be near a carbonyl, which is part of the ester, 2.1 to 2.6. We observe that here, where signal B is close to 3. So most probably, the CH2 is directly adjacent to not only the ester, but the alkene as well. Now let's look at signals D, E, and F, which are part of the alkene because we have complex splitting. The reason why we observe complex splitting is because these protons here, A, B, and C, don't have the same coupling constant. In the isopropyl group, we can easily apply the n+1 rule because the coupling constants are very similar between this carbon and this carbon, more specifically in reference to the hydrogens that are bound to them. If we have similar coupling constants, the n+1 rule works perfectly. But when we look at protons A, B, and C across the alkene, they don't have the same coupling constant. So the difference in coupling constant means we apply the n+1 rule individually. Now remember, we said in signal B, in reference to these two protons, it's most probably close to the alkene and ester. Let's imagine that these two protons are located right here at this carbon. So for proton A, we have two neighbors to the right, and we have two at the left, which have different coupling constants. So for proton A, the splitting pattern would be doublets of triplets. Now with signals E and D, doublets of doublets, this structure is still valid. If we look at proton B, it has one geminal neighbor, which is a doublet. It splits that into two signals. And it has a trans partner, proton A, which will split it into another doublet. So proton B would be a doublet of doublet. The same goes with proton C. Now that we've confirmed the protons bound to the alkene, we just need to confirm these two protons right here bound adjacent to the alkene that we did here. It's a 2H doublet because it only has one proton neighbor. And with this structure that we drew here, it's satisfied because these two protons are only adjacent to proton A. Now let's take a step back and look at all the carbons that we found. We had 3 in the isopropyl group. That was confirmed by signals A and C. We had another carbon here bound to 2 protons. That was signal B. That's a total of 4. And we said that it's close to the alkene and ester, most probably sandwiched in between. So if we add 3 plus 4 and these two, we have 6. And if we counted this carbon here as the alkene carbon, which is right here, and put in the terminal CH2, which is part of the pi system, that would equal 7 carbons. So let's try to put the structure together. We said we had an ester, so let's draw that in first. Now the only thing to determine is to see what R1 and R2 is. Basically, do we have the isopropyl towards the right, directly bound to the oxygen, or towards the left, which is directly bound to the carbonyl carbon in the ester? In order to understand why the isopropyl is indeed towards the right, we need to account for signal C, which is abnormally high in terms of frequency. We said that this hydrogen is located right here. And the only reason why it's so high in terms of parts per million, in terms of its frequency, is because it must be near electronegative atoms. So we can conclude that the carbon bearing that proton is directly bound to the electronegative atom here. If we count up the number of carbons we have now, 1, 2, 3, 4, 3 are remaining. So R2 must be a propene group with the alkene terminal. Now the final step is just to label the location of each signal from the proton spectra. So we said signal A was the integration of 2 methyls, so those would be right here. We said that the 1H septet here, located around 5 parts per million, was signal C. This CH2 group here would be signal B. This proton here would be the doublet of triplets. And because this trans proton has a higher coupling constant in the alkene, it would take signal E, whereas this one would be signal D.